Hello everybody, I'm back with another math video on how to conquer limits for Calculus 1. Generally speaking, the first thing you want to do is directly substitute. Directly substituting in a limit will give you one of three different results. The very first result will be a real value, aka you're done. It could be 0, it could be some rational number, all sorts of fun stuff. You can just directly substitute, and if you get a number, you're good. The second scenario here would be 0 over 0. This is not a percent sign. And basically what happens is if you get 0 over 0, you need to simplify that mess. It is messy, you need to simplify it. I'll go over some simplification techniques on the next slide. And lastly, if you get not 0 over 0, that means the variable is approaching a vertical asymptote. And this can be anything here. So let me see if I can do this. Like 3 over 0 or negative pi over 0. That means you're approaching a vertical asymptote. And again, I'll go over that technique in a couple slides from now. If you end up with 0 over 0, there are a few ways to simplify the expression, aka mess, so you can then directly substitute and get like a real valued answer. The first way would be to factor and cancel, and normally that is the correct choice when you have either a quadratic or a cubic, either in the top or the bottom of a fraction and a linear in the other, or you could have a couple quadratics, just basically polynomials. If you have factorable polynomials, this is what you're going to want to check. You can multiply by the conjugate. And this is generally good for when you have a square root involved in your limit somewhere. And of course, one thing I guess I'm not stating very clearly here is that these are all rational expressions I'm talking about. You have to get after direct substitution, you have to get a 0 in the top and the bottom of a fraction. Well, then you'll have to have a fraction involved and the square root involved somewhere within that fraction. Lastly, you can have good old-fashioned algebraic elbow grease. And you'll use this, you'll use algebra when you have fractions in fractions. You can either have a fraction or two in the top or the bottom of a larger fraction, or if you have a single term denominator. Let's take a look at an example of each of these. All right, everybody. First example with limits, the first thing that you are supposed to do is double check direct substitution. That's the very first thing you should do. So let's go off to the side here. I'm going to substitute 5 in for all of the x's, like this. In the numerator, I know 5 squared is 25. I know I can add 5 to that and get 30. And then I'll be subtracting 30, so I know the numerator will be 0. And in the denominator, I know that 5 cubed is 125 minus 125 is 0. So yep, 0 over 0. That means we have to do some sort of simplification. Take a look at this example here and think about which method you would use. All right. Hopefully that was enough time. This will be factor and cancel. And my clues here is that I just have some polynomials in the top and in the bottom. So what I will do is I will factor the top and factor the bottom. So here's the numerator and denominator both factored out. And if you are having trouble understanding how the denominator here factors into the denominator here, go ahead and search YouTube for factoring difference of cubes or factoring sum of cubes. This one in fact is a difference, but you can also factor a sum of cubes. Regardless, back to the limit, we see that the limit as x approaches 5 will equal x minus 1 times x minus 5 all over x minus 5 times x squared plus 5x plus 25. From here, you'll notice that the x minus 5s will reduce, so that, and that leaves us with the limit as x approaches 5 of x minus 1 all over x squared plus 5x plus 25. We've done exactly what was supposed to be done. We factored and then canceled. And so now what that means is we can substitute in the value. So that means we'll take the 5 and we'll substitute it in here, here, and here, leaving us with this expression here. And from here, it's pretty simple. 5 minus 1, that's 4. In the denominator, 5 squared is 25. 5 times 5 is 25. 25 plus 25 plus 25 is 75. And we're done. One thing before I move on to the next example about limit notation, this stuff going here. It is super important that you continue to write the limit notation as you go through your exercise. And here's the biggest clue. Students say, well, I don't want to keep writing it. No, keep writing it. It's mathematically correct to keep writing it. However, once you make your direct substitution, like we did in this step here, then you can stop writing it. You notice I've stopped writing the limit notation here. All right, let's take a look at the next example. I think the first thing that we're going to have to do is check to see if you get a 0 over 0 when you do this. So I'm going to do this off to the side as m approaches -2. So I'll have, let's see, 1 over -2 plus 1 over 2 all over 2 plus a -2. Well, all this first fraction does here is it becomes a -1/2. -1/2 plus 1/2 is 0. And in the denominator, 2 plus a -2 is also 0. Yep, 0 over 0. Okay. What do you do? How would you approach this? Which method would you use? Go ahead and pause the video, think about it. I'll be back in 5 seconds. Okay, so here I see there are fractions in the numerator of another fraction. And this fact tells me that I would be using algebraic elbow grease, or just algebra. Now there were a couple different versions underneath that algebra heading, the first of which was fractions within fractions, and the second one was a single term denominator. So this is clearly the first one, and when you have fractions, the general consensus among students ends up being, I do not like them. Is there a way we can get rid of the fractions? Usually ends up being the thought there. So in this case, yes, we can get rid of the fractions, but not all of them. We can get rid of these two fractions up here, but not this fraction here. This fraction is inevitable. It will be there. So how do we get rid of these fractions? Well, the first thing that you should do is find the LCD of these two fractions. So I have an m and I have a 2. And normally it'll just be the product of those two. So 2m. All right. What do you do with this LCD? Well, you're going to multiply the big fraction right here along the same line. You're going to multiply by 2m in the numerator and 2m in the denominator. And you can see that there's going to be some distribution happening here. The only place that you should distribute is the side of the fraction where there are fractions. So I see in the top, there are fractions. In the bottom, there are no fractions. So I'm going to distribute the 2m up here, but not down here. You'll see why in just a minute. So when you make that distribution, it'll look like this. There you So to walk through that very quickly, when you multiply 2m to 1 over m, the m's will reduce, leaving you with just a 2. Plus, when you multiply 2m to the second fraction, the 2's will reduce, leaving you with just m. So now you can see that the 2 plus m in the numerator and the 2 plus m factor in the denominator will reduce. However, if you distributed this 2m in the denominator to each term, you would not be able to see that as easily. So you only want to distribute the 2m or the LCD wherever the fractions are. All right, so I said that these reduce away. That leaves you with the limit as m approaches -2 of 1 over 2m. From there, you can make that direct substitution in for m, and 2 times -2 in the denominator is -4. So -1/4 or 1 over -4 would be your answer here. One extra little warning here about these limits with fractions in them, like fractions within fractions. The fractions don't always have to be in the numerator. The fractions could be in the denominator. The fractions here, the little ones, could have multiple terms in the denominator. There are all sorts of different variations of this. But if you follow the process I went over right here, you will be successful in finding those limits. Let's take a look at a couple more examples. All right, last two examples for this video. You can see in this example it's a bit monstrous, but we should always check direct substitution first. I can promise you pretty easily that the denominator here will be 0. There's nothing to figure out there. But in the numerator, each time instead of parentheses we have 3 minus 0, it's just going to be 3. So we've got 3 squared, which is 9, plus 3 is 12, minus 12 is 0. Okay, so pause the video, think about which method you would use for this. All right, here in this example, I'm thinking I'm going to have to use some more elbow grease. And my clue is that I have a single term down here in the denominator. It's just h. And the single term also happens to be the variable that is being used in this limit. That being said, how are you supposed to figure this limit out? Well, the only way to figure out this limit is to distribute everything out in the numerator. So I've got to distribute this out, distribute the 1 here, technically speaking, and then combine all the terms up here. So after you distribute this out before you collect like terms, it'll look like this. There we go. The squaring of this binomial will yield these 3 terms, plus 3 minus h, minus 12. You can simplify the constants here. So 9 plus 3 is 12, minus 12 is 0. We can also combine these h terms here. And when you combine all of this, you'll end up with the limit as h approaches 0 of h squared minus 7h in the numerator all over h. From here, there is a very sneaky factor and cancel happening. You'll notice that each term in the numerator has an h in it. So if you common factor an h, you can then see that the h's here will cancel, leaving you with the limit as h approaches 0 of h minus 7. You can then directly substitute the 0 in for the h and get -7. So that's it. Like, this is the quote-unquote trick. The trick is remember your algebra. So again, the process here, when you have a single denominator, that is the variable that is being used in the limit. Multiply everything out in the numerator and collect like terms. Common factor that variable from the numerator. You'll cancel that variable, and then you can make your direct substitution. The last example here. Here we go. this is a doozy, but not impossible. So when you look at this, you'll notice that we have the limit as p approaches 3 of 3 minus p over the square root of p plus 6 minus 3. Again, off to the side, we have to check really quickly that this will equal 0. So 3 minus, substitute 3's in for all the p's. In the numerator, 3 minus 3 is 0. In the denominator, 3 plus 6 is 9. The square root of 9 is 3. 3 minus 3 is 0. Cool. The check works. It's 0 over 0. Pause the video. Think about which method you would use. I'll be back in 5 seconds. Okay, for this one, the big clue here is that I've got a square root and a second term being added or subtracted to or from that square root. And this denominator could have been written a bunch of different ways. For example, it could have been written like this, -3 plus the square root of p plus 6. The square root could have been negative square root of p plus 6 plus 3. It could have been 3 minus the square root of p plus 6. All of these different variations of this denominator here would have been the same clue. I see a square root term with another term being added or subtracted. This is your clue. You want to multiply by the conjugate pair. And before I get into that, I need to state also that this, or any of these, could have been in the numerator of the fraction as well. So just beware of all that. So here, we want to multiply by the conjugate pair. And the conjugate pair just means multiply by the same two terms. And we're going to use the pair of terms with the square root. So we're going to have the same two terms. This will be the square root of p plus 6 and 3. Square root of p plus 6 and 3. But we're going to change the sign in between the two terms. So if this were a positive, we would make this negative. If this is negative like it is, we would make this positive. Now, kind of like we did with the LCD example on the last slide, you only want to distribute the side that has the square root. So I only want to distribute things that are in the denominator here. And when you do that, conjugate pairs multiply really nicely. It's essentially, you'll square the square root here, which will give you p plus 6, and you'll square the 3 here, which will give you minus 9. So the next limit will look like this. There you go. From here, you can simplify the denominator positive 6 minus 9 to be p minus 3. Now, it's not immediately obvious how this is helpful, but if you think of this factor in the numerator as the negative of the factor in this denominator, and what do I mean by that? Well, the p has an opposite sign here, and the 3 has an opposite sign here. It is exactly the negative. So what that allows us to do then is it allows us to reduce away these two factors as long as we replaced it with a -1. So it'll be -1 times the rest of this here. All right, so let me get that written out. So this is the new limit here. The limit as p approaches 3 of the square root of p plus 6 plus 3. Then you can make the direct substitution here. You'll have 3 plus 6 inside the square root, which is 9. The square root of 9 is 3. Plus this extra 3 will give you an answer of 6. All right, so I didn't get to the example of the not 0 over 0. I will link a video right about now into this current video to lead you over to what happens if you get not 0 over 0. I hope this helps you with your understanding and limits for Calculus 1, and as always, Good luck.